And we have been solving partial differential equations. One example of which was the heated plate. Here was the Laplace equation, or the equation that governed the steady state temperature in this heated plate. In rectangular coordinates, x and y, x and y, and the plate itself was rectangular. And we could solve it using the product method, separation of variables, even if it was totally surrounded by some temperature on all sides, even if there were no zero conditions anywhere. What if the plate is round instead of rectangular, perfect circle? Well, that's where we will use a different coordinate system. That's what we're going to start doing, using a different coordinate system instead of rectangle. Everything we've done up to now was in x and y, rectangular coordinates. So for this case, we would transfer to polar coordinates. X equals r cosine theta, y equals r sine theta, like usual polar coordinates. And if you take this equation and do some partial derivatives and chain rule calculations, it's pretty long and tedious, but you would come up with this equation, its equivalent in polar coordinates. So this is our new Laplace equation in polar coordinates. So that's the equation that needs to be solved for the round heated plate, where r goes from 0, the center of the plate, out to some distance that's a constant. So it's a perfect disk, circular disk. Theta goes around 2 pi. And we'll say out on the edge, the outer rim, it's held at some constant temperature that's a function of the angle. In general, we're doing new coordinate systems, and two big things are going to crop up. One is we're going to get some ordinary differential equations that we didn't see before in rectangular coordinates. So we're going to need to extend our formula sheet. The second thing that's going to crop up is there are going to be new boundary conditions that are implicit. I'll talk about those. So let's see. So using the product method, that says we're going to take our function and split it up into functions of each of the two variables separately. Now our variables are r and theta, little r and little theta, or coordinates. Here's the equation. So rewrite it in this type of form. This first term will be r double prime theta, big R double prime theta. Here we have the 1 over little r times big R prime, big theta, etc. That's this line here is just the equation rewritten using the product version. Now we start doing some algebra to separate r's from thetas. First, we'll multiply through everything by r squared. This. At this point, we'll divide by big R, big theta. You get that. So we have them separated. Big theta double dot, the big theta double prime over theta equals a separating constant, and the R equation equals the same separating constant. The big theta equation then turns out to be this familiar second order equation that we've encountered before in rectangular coordinates. The R equation, it's a new one that we didn't encounter when we did rectangular coordinates. Let's look at that theta equation first. First, let's go back to the problem. If you take some point here, some physical point on a physical plate, theta is the angle up to that point, right? If I add 2 pi to the theta, I'm back to the same point. But it's not a different point on the plate, it's the same point. So our solution in theta must be 2 pi periodic in theta. So that is our implicit condition. So take this equation, go through the three cases as usual. Theta is negative, we'll set it to minus alpha squared. We get this solution. There is no way these quotient sins become a 2 pi periodic solution. Can't even make it a constant. A constant is 2 pi periodic. In fact, it's periodic in whatever period you want. So we reject this first case of negative lambdas. If lambda equals 0, we get this general solution. And if we just set b to 0 and we're left with a constant, that is 2 pi periodic. So we accept that eigenvalue, and its associated eigenfunction is just some constant. Then for the lambda positive case, here's the general solution. We've seen it plenty of times before. That is 2 pi periodic if these alphas are the positive integers. You can convince yourself of that down here. I'm not going to go through that. So our eigenvalues are the positive integers squared, and the eigenfunctions are these guys. Cosines and thetas and sines and thetas. Now, that gets us so far with the theta equation. Now let's look at the R equation. Let's skip this line for a minute. Well, it's going to turn out, well, here's our equation in R. Now we have a lambda, it's n squared, where now this n could be 0. That matches this equation, which we would have on a formula sheet. Remember, I actually have a formula sheet available to you. Email me and I can send you a PDF of it. And I talk about it in one of my other recordings. And it has a solution, one for when alpha is 0, and when the other one when it's not 0. So for the eigenvalue equals 0 case, we get that form of it, or this form in terms of little r. When the other eigenvalues, the positive integers squared, that matches this case. And we get this general solution. So these are the general solutions. Now let's bring up the second implicit condition. And that is, we can't have an unbounded solution. Remember, this is steady state temperature. It can't go off to infinity anywhere in your range of variables. And that holds for both the theta equation and the R equation. Let me go back a minute here. You can't, anywhere where on this plate, which means between where these values were in these intervals, solution must be bounded. So all the way from R equals 0 to R equals C, it must be bounded. And all the way around the plate, it must be bounded. And when I split up the function, that means each of these must be bounded within their individual range. For the theta equation, all our eigenvalues are constant, and these guys all stay bounded regardless. But for R equation solutions, what about the center of the plate where R equals 0? As R goes to 0, the natural log goes off to minus infinity. That's not bounded. So we need to set C2 to 0, or just say we reject this part of the function and we're just left with a constant. So now we have the corresponding function for R for the lambda equals 0 case. Eigenvalue equals 0. What about this guy? This is r to the minus n, or 1 over r to the n. Again, if r is 0, that blows up. The sky becomes infinite, unbounded as r approaches 0. So we set C4 to 0. We're just left with this part. And here's the summary then for all our eigenvalues. The eigenvalues came from the theta equation. Here's the corresponding functions for our solution. Now, like before, total solution is the product of the two individual solutions. U for the lambda equals 0 case was a constant times another constant, so we'll just call it a sub 0, some constant. And for all the positive integer cases, it was r to the n, which came from the r solution, and then this part, which came from the theta solution. And again, we sum all those up to n equals infinity. So here is our general solution that satisfies the partial differential equation itself, the implicit condition of 2 pi periodicity, and the implicit condition of boundedness. What it doesn't solve is the temperature on the outer rim of the plate. And there we do, just like we did before, we match it to the Fourier series we need to match it. So the temperature at the outer edge is where R equals that C. So we plug in C for R, and you get this. That must equal the function they gave us, which is the temperature around the edge. So we're going to expand that guy. Look at this thing. It's in the form of a full trigonometric Fourier series. So we'll expand this function in a full trigonometric Fourier series, not just a cosine function or not just a sine function, which is all we ran into with rectangular coordinate problems. So we match coefficients again. Big A sub 0 will be little a sub 0 over 2. The big A sub n times C to the n will equal the little a sub n's. And we have a formula for the little a sub n's. You can look up these formulas in a formula sheet. It's on my formula sheet again. So you know what the formulas are for these little a's and little b's for the Fourier series. So anyway, this is just like before. We're matching coefficients. So now we have, this was the solution, but now we have the big a's and b's. Big A sub n, or big A sub 0 will be, with little a sub 0 over 2, which was this. So we're done. And the formula for a sub 0 over 2. Big A sub n is this divided by C sub n. So you have this. Anyway, here's the summary. Here's the solution we had before. It matched everything except the outer edge requirement. And here's the big A's and B's, so you meet that outer edge requirement. What is it at the center of the plate? What's the temperature at the center of the plate? At the center of the plate, R is 0. R to the 0 for, or R to the n, 0 to the n, I should say, or n equals 1 and up is 0. So this whole mess goes away, and I'm just left with a sub 0. Here's the formula. So there's the temperature in the middle of the plate. And that's the round heated plate problem, which is our first foray into other coordinate systems, solving partial differential equations in other coordinate systems.